Black holes are often described as cosmic destroyers, places where matter is crushed, light disappears, and everything that falls in is erased forever. This image is powerful, dramatic, and deeply misleading. Physics now suggests something far stranger. Black holes may not destroy reality at all. They may store it, not inside, but on their surface. And that idea forces a complete rethinking of what space, information, and existence actually are. The story begins with a problem that physics cannot ignore. According to general relativity, anything that crosses a black hole's event horizon is lost to the outside universe forever. Information about its state can never be recovered. But quantum mechanics forbids this. In quantum theory, information cannot be destroyed. It can be scrambled, hidden, spread out, but it must be preserved. These two principles collide at the event horizon. One theory says information vanishes. The other says it cannot. Both theories work extraordinarily well everywhere else. At a black hole, they disagree completely. This is not a technical detail. It is a fundamental contradiction. For decades, physicists argued about which theory would give way. Many believed black holes truly destroyed information, even if quantum mechanics protested. Others suspected that our understanding of black holes was incomplete. The debate remained unresolved until a radical idea began to emerge. What if the information does not disappear? What if it is encoded on the event horizon itself? The event horizon is not a physical surface. You cannot touch it. But it acts like a boundary. From the outside, everything that falls toward a black hole appears to slow down and freeze near the horizon. Signals become redshifted, stretched, weakened. To an outside observer, nothing ever quite crosses. This strange behavior hinted that something special was happening at the boundary. Physics followed that hint. Calculations revealed that black holes have entropy, not metaphorically, but quantitatively. Their entropy is proportional to the area of the event horizon, not the volume inside. This was shocking. In every other system, entropy scales with volume. More space means more possible states. Black holes break that rule. They behave as if all the information they contain is stored on their surface, not inside, on the boundary. This led to one of the most profound ideas in modern physics, the holographic principle. The holographic principle says that the information content of a region of space can be fully described by information encoded on its boundary. Just as a hologram encodes a three-dimensional image on a two-dimensional surface, reality itself may be encoded on lower-dimensional boundaries. In this view, the three-dimensional world you experience is not fundamental. It is a projection, a representation of information stored elsewhere. Black holes forced this idea into existence. They made it unavoidable. If information is preserved and black holes have maximal entropy, then the horizon must store everything that falls in. Reality does not end at the horizon. It is recorded, but this raises an immediate question. If information is stored on the horizon, what happens to the interior? According to relativity, an infalling observer crosses the horizon without noticing anything special. Nothing dramatic happens locally. Space feels normal. Time flows. Physics appears unchanged. This creates a paradox. From the outside, information is stuck at the horizon. From the inside, information falls through. Both descriptions seem valid, and they contradict each other. Physics resolves this not by choosing one perspective, but by accepting both. This leads to the idea of black hole complementarity. Complementarity says that no single observer can access both descriptions. Outside observers see information encoded on the horizon. Inside observers experience a smooth crossing. There is no contradiction because the two viewpoints can never be compared. Reality is consistent, but only locally. Global consistency is replaced by relational consistency. This is unsettling because it breaks the idea that there is a single, observer-independent description of what is happening. Black holes do not just challenge gravity, they challenge objectivity. The deeper implication is that space itself may be an emergent concept. If information is stored on boundaries and interior space is a derived description, then volume is not fundamental, depth is not basic. What feels like inside may be a convenient fiction generated by information patterns. The universe might not be three-dimensional at its core. It might be fundamentally lower-dimensional, with extra dimensions appearing as effective descriptions. Black holes reveal this because they saturate the maximum amount of information that can be stored in a given region. They are not just objects, they are limits. Limits on information density, limits on entropy, limits on what space can contain, and limits reveal structure. When you push a theory to its limits, its hidden assumptions surface. Black holes push physics harder than anything else. They force gravity, quantum mechanics, thermodynamics, and information theory into the same conversation. And the conversation changes everything. If black holes store information, then evaporation becomes meaningful. Hawking radiation is not random noise. It carries information subtly encoded in correlations. Over immense timescales, information leaks out, scrambled beyond recognition, but not destroyed. The black hole is not an eraser, it is a processor. It takes information in, mixes it, and releases it. Reality passes through the black hole transformed, not annihilated. This reframes destruction itself. When something falls into a black hole, it is not lost. It becomes inaccessible for a time. And inaccessibility is not non-existence. Physics increasingly treats information as the most fundamental currency. Matter and energy are ways information manifests. Space and time are ways information is organized. Black holes sit at the intersection of all these ideas. They show that information is conserved even when space-time itself seems to tear apart. This leads to a disturbing thought. If black holes store information on their boundaries, and if the universe itself has boundaries, then the entire universe may be holographic. Reality as you experience it could be a projection of information encoded elsewhere. You would not notice this any more than a character in a hologram notices the film it is encoded on. The interface would feel complete, solid, self-contained. The idea that black holes store reality also changes how we think about death and permanence at a cosmic scale. Nothing is erased. Events are not wiped out. They are recorded in the structure of the universe. Even in the most extreme conditions, reality keeps track. This is not a comforting idea. It does not promise recovery. Stored information is not accessible information, but it undermines the notion of absolute destruction. At the deepest level, the universe seems allergic to erasure. It preserves structure even when form disappears. Black holes are the ultimate test of this principle. They appear to destroy everything, yet they obey deeper rules that prevent true loss. And in doing so, they expose a radical truth. Reality is not built from objects sitting in space. It is built from information constrained by boundaries. Space, depth, and volume are emergent conveniences. Information is what persists. Black holes do not end reality. They reveal what reality is made of. And once you see that, the idea of space as a container starts to feel like an illusion. The universe is less like a box full of things, and more like a network of information encoded on surfaces. Black holes are not exceptions to this rule. They are its clearest expression. This is Veritas Labs, where truth is tested